In the case of Navier-Stokes or ring of fire, called Kuramoto-Shibashinsky by the professionals, we can talk about energy. And it's a very simple idea. When you look at Navier-Stokes equation, we can write it, or ring of fire, one-dimensional version. We can write a derivative in time in terms of some kind of time-dependent potential, where x takes care of all the spatial things. So V can be written as 1/2 q squared. First spatial derivative of our velocity function. Remember, this is one-dimensional velocity. Third derivative. And if you take one derivative more, you just get the Kuramoto-Shibashinsky equation before. But notice this term. This looks like kinetic energy. Because in fluid dynamics, this would be a velocity of a particle of a little volume of fluid. If you normalize it in such a way, say we have constant density, choose this density to be 1, this looks like 1/2 m squared times m times velocity squared. So you can think of it as kinetic energy. Then we can compute the mean kinetic energy, or the space average of kinetic energy at time t. I can call this whole function an energy function. So let's define E, an integral over the domain of V of x and t. And now we observe, because we are on a periodic domain, the gradient, first derivative of our observable, and compute it on this domain, then we can do this integral, but because it's periodic domain, initial point is same as the final one, so the gradient is clearly 0. And we can also move derivatives around using integration by part and periodic boundary conditions, so we can take two functions, let's say A and B, gradient moved on the other function. So now we observe that the two extra terms in this definition of energy are of that type. So integrated over the domain, they'll give 0 contribution. And we find that the energy so defined is simply the value of the kinetic energy, u squared over 2, averaged over the domain. That gets rid of the space dependence in u, but not time dependence. So this energy is time dependent.